Awesome. Yeah, so my name is Pratik Sathe. I'm a physics PhD student at UCLA. And the focus of my work has been on theoretical condensed matter physics, which is the quantum mechanics of single and many particle systems. So I've been quite curious about how useful quantum computing is and how good the current computers are. And so this project has been a really good way to dig in. So I'm going to talk about the work that I did over the summer. And it was about benchmarking using this algorithm called the quantum approximate optimization algorithm. So I'll start with a very brief background. So we are all here because we're excited about quantum computers. So it's very important to figure out how reliable they are. And the approach taken by the quantum consortium for this was application oriented. So benchmark using useful algorithms. Now, last year, a manuscript was put up presenting this suite of benchmarks. And some of the algorithms that were used for benchmarking were textbook algorithms like Grover's algorithm and phase estimation, etc. So the good thing about these algorithms is that we have a very good theoretical handle on how well they perform. But the bad thing is that we have found that to get anything useful out of these, we need lots of qubits and they need to be of good quality. Both of these things we do not have at the moment. However, there's a class of algorithms which provide some promise to deliver even with noisy qubits. And a lot of the research it indicates that we might even have a quantum advantage with these algorithms. So this class of algorithms is called iterative hybrid algorithms. And the work we did over the summer, me and the other intern, Josh, we enhanced the benchmarking suite to benchmark algorithms of this type. So we chose an algorithm, a very famous algorithm in this class of algorithms. It's called the quantum approximate optimization algorithm, or QAOA in short. And it solves the so-called combinatorial optimization problems. So the best way to explain this is to look at an example. So consider binary variables, S1 to Sn. So each of them are 0 or 1. And let's say we have a cost function which consists of sum of products of these variables. The objective is to find a bit string, essentially, which will minimize the cost function. Now, this problem is very easy to state, but it's hard to solve. And even the best classical approaches are heuristic. They only solve the problem approximately. So a question that one can ask is, can we get some speed up if we use quantum computing? And one such proposal was an important proposal was put forth in 2014 as the QAOA algorithm. And as I said, it's a hybrid quantum classical algorithm, meaning some part of it is quantum, some part of it is classical. And there has been a lot of research on this algorithm and similar algorithms. And it looks like these algorithms may actually work pretty well. So I'm going to briefly talk about what it looks like. So this is a circuit. You might see something like this when you search for QAOA, but it's much nicer to abstract away the details and look at a really short summary of what the algorithm does. So you have a circuit and you have some measurements at the end, and you have a bunch of gates over here. The main point is the circuit is parameterized by some real parameters, beta 1 to beta p and gamma 1 to gamma p. And corresponding to each parameter, each value for these parameters, you have a circuit. Now, the outcome of the basic idea of this algorithm is that each circuit, it corresponds to a probability distribution over possible answers to the problem. And the objective is to find angles which make sure that the probability distribution is highly peaked at the correct answers, because there can be more than one answer. So here's what the loop looks like. You choose some initial parameter values, you create the circuit corresponding to it, measure it many times, and obtain an expectation value of the cost function. Then you use a classical minimizer routine, such as a gradient descent algorithm or something else, in order to obtain better angles. And if you find that you have converged, you stop at that point, or you go back and repeat. So before we assess the quality of this algorithm, it's first important to check whether our quantum computer is doing what, when it implements a circuit, does it actually implement it well? So that's captured by the fidelity measure. So this is from the framework that existed before we started working on it. And as you can see here, as the problem becomes larger and larger, the fidelity goes down. And there's a very nice way of capturing that in a width versus depth volumetric positioning plot. But this is not enough in order to capture the intricacies in iterative hybrid algorithms. So since these algorithms are heuristic, we need to come up with appropriate measures for quantifying the result quality. And there are lots of hyperparameters, and it's important to understand what effects they have on the performance of the algorithm. So my contribution to this project has mostly been in figuring out the right metrics and visualizing them in a useful manner, and developing code and integrating it into the existing framework so that it fits well and allows us to run it on simulators as well as hardware. So I'm going to show a few plots which are quite pretty and we believe also very useful. So this plot over here is what we call an area plot. So this shows how the quality of the result improves as a function of the iteration number. So each box is an iteration. And as you move from left to right, you see the time it takes for the quantum execution. So we chose a problem called the max cut problem because it's been thoroughly analyzed theoretically. And this is a snapshot which tells you how the width of how the size of the problem affects the time taken, how the quality at the end of the algorithm depends on the problem itself, and so on. So this is another pretty plot, also we think very useful. So on the previous plot, we saw that the colors were approximation, they were used to show the approximation ratio. So that's one number which captures the performance of the algorithm. Now, various other statistics have also been proposed in the literature. So we have developed a mechanism in order to be able to plot that, plot all of these metrics and also the entire distribution of outcomes. So it's not enough time to describe this in detail, but that's one of the useful things you can do with it. Now, here's yet another example of what the framework allows us to do. So in the simplest case for one of the simplest problems, you only have two parameters, beta and gamma. And plotted over here is the cost function landscape. So red is bad, green is really good. And what the optimizer will try to do is it should try to take you to the green regions as much as possible. And shown over here is what the framework allows you to do. So let's say you start at location S1, the optimizer takes you through this dashed line trajectory and you end up at F1. So the square is the best value, F1 is pretty close to it. But if you start somewhere else, also chosen at random, you don't necessarily end up at a really nice place. So this plot highlights that initial conditions matter. So this is just one of the examples of the type of analysis you can do. You can analyze various types of effects in detail. And that's one of the key points I want to convey here. We have a framework which is openly accessible. Anyone can download it and run it in order to analyze the various facets of this algorithm and see if the hardware works well or not. So just some future plans. So we are preparing a manuscript on this. And we plan to submit it for peer review and post it on archive in a couple of months. I should also emphasize that Josh, who's the other intern, is going to talk about how he brought together this code and put it together in order to be able to run it on actual quantum hardware. Now, we also want to apply this technology that we have developed to similar algorithms like the variational quantum eigen solver. We believe it can be translated quite straightforwardly to other iterative algorithms. And as I said, I'm planning to I'm doing a PhD. I plan to defend in a few months in spring of 2023, and I hope to continue working on quantum algorithms and quantum information science. So just this is my last slide. I really learned a lot during this internship. I got to know quite a bit about what's happening in the field of quantum computing. I got to collaborate with researchers, engineers, and I sharpened my software engineering skills. So I would highly recommend this internship experience. And thanks a lot to Tom Lubinsky, who's been a mentor and the leader of this project, to Jonathan for support and guidance, and to Josh for being a wonderful collaborator. So thank you.
Very nice presentation, Pratik, and that's a good segue to Josh. For the audience, please hold your questions and comments at the end of the hour. We'll have ample time for feedback and discussion.
Hello, can you see and hear me?
Yes, sir.
Great. So I'll go ahead and get started. So yes, like Pratik said, hi, I'm Josh, and today I'm going to be talking about implementing application-oriented performance benchmarks for hybrid quantum computing. So just a quick brief outline. I'll give a brief introduction to myself, go over the goals of the project. Pratik already hit a lot of the main points, but I'll quickly go over how hybrid quantum algorithms work. And then we'll talk about what are known as containerized execution environments that are necessary to run hybrid algorithms on actual hardware. We'll discuss circuit transpilation and parameterization. And then finally, we'll discuss how we integrated the hardware runs into our benchmarking framework. And then I'll talk about future work. So about me, my name is Josh Apanavicius. I graduated with a master's in quantum information science from Indiana University, Bloomington last month. And my topic of greatest interest is applications of hybrid quantum algorithms. Now, jumping into the main goal of this project, I'll be discussing how we implemented our hybrid quantum algorithm benchmark to run on actual hardware. My specific goals were the following: implement our quantum approximate optimization algorithm for max-cut benchmark to run on actual hardware, as well as how we optimize this implementation with the use of parameterized quantum circuits. And due to time constraints and the fact that Pratik already hit on a lot of the specifics, I won't go into the details of the actual algorithm or the problem, just focusing on the implementation and parameterization. So first, some quick background on the important aspects of the QAWA algorithm. Mainly, QAWA is a hybrid algorithm, and the term hybrid refers to a process where the final result is obtained through the use of both a quantum and a classical computer. Generally, the workflow is as follows. You prepare a state on the quantum computer, run that circuit, get the results, and feed them into a quantum computer. Use this to create a new state, and then repeat that process until completion or failure. And as Pratik mentioned, QAWA has two main parameters, beta and gamma, and these are the ones that we will be optimizing. Now, the main problem with executing or implementing hybrid algorithms on actual hardware is the very nature of them. It's that they're iterative. And the hybrid algorithms generally need a lot of iterations to converge to a suitable tolerance. In our case, the QAWA for max cut usually takes around 15 to 30 iterations on average. Then when you submit these to actual hardware, you have to submit a circuit for each iteration. And due to the high demand of QPU time, users have to be placed in a queue or a line for each submission and waiting for previously submitted jobs to complete. And with quantum computing being such a rapidly growing research area, there are a lot of users right now, and this can run up queue times on the order of hours, days, and even weeks. And just to kind of highlight the point, say that our QAWA just takes the minimum of 15 iterations to converge, and on average a queue time of around a day. That'll take one full QAWA run around 15 days to complete. And this quickly becomes intractable, but luckily for users, there is a clever solution to this. Many hardware providers offer a service known as containerized execution environments. In our case, we primarily used IBM's implementation known as Qiskit Runtime. Here's just a quick or a brief graphical depiction of the runtime workflow. So containerized execution environments allow users to continually submit circuits back to back in their iterative workflows. This is accomplished by users uploading their own programs, constructing and implementing their hybrid algorithms before submitting a job to execute the circuits. Then the user submits a job to their desired backend, as well as specifying the previously uploaded program they want to run on that backend. And once the user submits a job, they're still initially subjected to the queue. However, once the job arrives at the QPU, it iteratively continues execution until completion. And so now that's the main aspect. Now actually integrating it into the benchmark suite. While Qiskit Runtime is extremely useful, it requires a lot of steps to upload your program and actually run your jobs. I think the largest implementation or the largest limitation, especially for large and complex projects like our benchmarking suite, is that programs are only allowed to be a single file. And our benchmarking framework is quite complex. It has a lot of modules. That's one of the main selling points of Python, is how modular it is, and we definitely take advantage of that. And so to actually get this running, we had to do a lot of pre-processing. For example, we had to concatenate and filter 4 separate files, having to do with everything from actually executing and calculating, combining the metrics. This add main is specific to runtime. They force you to have an actual function titled main to actually kind of handle the execution, and then obviously the benchmark. And then we actually, since this was under such rapid development, we actually decided to do this programmatically, because we also had to remove unnecessary imports. Anything that was saved to files, we had to remove because we didn't have access to a file system on the runtime server. Just a lot of things that kind of really compounded and made it somewhat complicated, but it still, we wouldn't be able to do it without it. So it was worth it in the end. So now that we're able to actually run our benchmarks on actual hardware, I'm going to talk about optimizing our implementation. And so the main optimization comes at the circuit transpilation level. So hybrid algorithms require the construction and execution of a lot of quantum circuits. And when a user builds a quantum circuits, or when they build a quantum circuit, they're free to use any unitary operator, measurement, or reset operations. However, when actually running the circuit on a real quantum device, this flexibility is actually quite limited. The main limiting factors are device connectivity, or the physical interactions between the qubits, how that specific device implements multi-qubit gates, and also the actual control electronics of the machine. All of this kind of translates into a specific quantum computing device can only natively support a handful of quantum gates and non-gate operations. Therefore, most circuits have to undergo a series of transformations that make them compatible with that given target device, as well as optimize them to reduce the effects of noise on the resulting outcomes. Qiskit, along with many other software development kits, allow for users to define their own custom passes for any type of optimization or transformation, and can be the topic of many discussions. I mention it here because it is a necessary and important part of the benchmarking process, because it can be fairly computationally expensive, and we do take this into account in our benchmarks. And the main optimization for circuit transpilation is the use of parameterized quantum circuits. And so in our naive non-parameterized workflow, at every iteration, the classical optimizer constructs, transpiles, and binds the beta and gamma parameters that Pratik spoke about before running the circuit. And this implementation is very inefficient. Each circuit can have a lot of parameters depending on how many rounds you do. And also, just due to the similarity of the circuits, they're all completely identical except for the parameter binds. So we're doing a lot of excess operations for essentially no reason. And that's where the parameterization comes in. So with a parameterized workflow, for each iteration, we only have to create and transpile a circuit one time. And then on each subsequent iteration, all you have to do is bind those new parameters. Because like I said, the circuit is identical to previous iterations, except for the parameter values that the classical optimizer spit out. And so now that we have all that working, we'll go into actually benchmarking the execution. So now, due to the hybrid nature of the algorithm, our benchmarking efforts are primarily separated into two separate domains, quantum and classical. So for the quantum aspect, we are interested in how long it takes the quantum processing unit to run the circuit. This is primarily limited by the actual hardware, and due to this, no amount of classical optimization techniques will improve these times, which we'll see in the preliminary results. And for the classical aspect, we're concerned with the optimizer time, namely how long it takes for the classical optimizer to converge, as well as wall clock time, which measures how much time has passed as if you're looking at the clock on your wall. And this kind of includes the time to construct, transpile, and assemble the circuits for execution. So the results outlined in these plots are from runs performed on the IBM machine Jakarta, both with and without parameters. So just kind of breaking down the plot, the length of each of these individual rectangles corresponds to the amount of time taken for that specific circuit to run. So in this example, we had 30 iterations, so there are 30 squares here. And as you can see, the quantum execution time is mostly unaffected by the use of parameterization, and this was expected. Just a quick note, unfortunately, these runs were executed with a bug in the code that resulted in poor results. The color of the rectangle corresponds to the accuracy of the result, but the bug did not affect the actual performance of the implementation, so the quantum execution time wasn't affected. So we're mostly concerned with the time, not the color of the box. Now moving to the wall clock time. So like I said, the wall clock time measures how much time has passed as if you were looking at the clock on your wall while the program is running. In our case, the wall time informs us of the time to construct, transpile, and assemble circuits for execution on hardware. Now, as you can see, our parameterized implementation can produce a substantial reduction in wall time. This is because transpilation can be a computationally expensive task, and the use of parameterization greatly reduces the number of times we have to transpile the circuit. However, we have seen a large amount of variability in the results due to the intrinsic differences of the hardware. To mitigate these discrepancies, we simply need more data. However, this has proved challenging because while runtime has allowed us to actually run our benchmark in a reasonable time, the initial queue time has still been on the order of many days. And we have also had a lot of issues with internal service errors, meaning an error incurred on the actual server side that we couldn't do anything about. And that concludes the work. Just kind of as a summary, we were able to successfully run our hybrid algorithms in a reasonable time on actual hardware with the use of containerized execution environments. And we were able to show preliminary performance gains with parameterization of the quantum circuits. Now just a brief look towards the future of this work. We want to investigate the impact of third-party circuit optimization implementations, specifically PyTicket and TrueQ. We want to add some more SDKs, specifically Q#. We want to run it on different hardware architectures, particularly trapped ions. We also want to add some other iterative algorithms like VQE and QML benchmark. And then lastly, I just wanted to thank my colleagues and mentors for their mentorship and giving me this opportunity to help advance the benchmarking project. And with that, I'll be open for questions.